In the previous lecture, we looked at the very influential mechanical philosophy of the 17th century. There were a lot of good things about the mechanical philosophy. It makes the world rational. It promises to explain a lot of phenomena by a minimum number of explanatory principles. But it's also embroiled in a bunch of logical, theological, and philosophical objections as well. In this lecture, we're going to look at another way of viewing the world, that of vitalism, and also look at how vitalism and mechanism can be hybridized to form other systems. Well, generally we think of mechanism and vitalism as being opposite ends of a spectrum, and it's fine to think about things that way. The mechanism sees a lifeless world that functions as a machine. It's totally passive. There are no active forces in the world. It's only acting based upon trajectories, collisions of lifeless pieces of matter. On the other end is vitalism, which sees a living world, a vital world, a world filled with forces, an active world, a world where life is everywhere, where life doesn't actually have to be explained in a sense because it is everywhere. Whereas in a mechanical worldview, life becomes something that needs to be explained by some other kinds of principles. As I say, it's all right to think of these as opposite ends of the spectrum, but I don't want you to start thinking of mechanists on one side and vitalists on the other, and there being no common ground between them. Because as I said previously about the 17th century, it's this time when there are all sorts of views and everyone is coming up with new ways of approaching the world, so there are lots of intermediate steps between those two. Think about them as extremes, but remember that there's a continuum between the two to a considerable extent. But vitalism has a bit of a bad cachet nowadays. We tend to think of vitalism as being somehow non-scientific, as an appeal to non-scientific forces. But it doesn't actually have to be that way. Vitalism has a certain common sense of its own. It's very hard, I think at least it's very hard for me sometimes, to look at the growth of a tree. You plant a tree and you watch it grow from year to year. You watch a dog playing on your carpet in front of the fireplace. It's hard to think of those as lifeless machines that are just functioning by the collision of atoms and by mechanical forces. There's something commonsensical about putting vitalism back into the world. Well, Descartes' world is perhaps the one that is most rigidly mechanical out of all the mechanical philosophers. Only man has an immaterial, living soul. He's the only vital thing in the world. Everything else is dead and mechanical. These mechanical and vitalist systems existed concurrently, and what we'll find here is as we start looking at individual characters, the lines between them become more and more blurry. We find people importing mechanical things into vitalist systems, importing vitalist things into mechanical systems. The life sciences and medicine, I think, are an important locus to examine the issue of vitalism, because those are talking about living systems, not like astronomical bodies or falling bodies in physics. And so vitalism becomes particularly important in life sciences and in medicine. Let's look at a little bit of background to the medical sciences of the 17th century. Because the medical sciences, like astronomy and physics, underwent considerable change in the Renaissance and in the scientific revolution. A key development was a new interest in anatomy. A climax of this, or a high point of this, was Vesalius's work on the structure of the human body, De Fabrica Humani Corporis. Interest in anatomy had been on the increase since the late Middle Ages. Many more dissections being done, many more anatomical studies, particularly in Italy. But Vesalius's book is published in 1543, outlining the anatomy of the human body. Same year, you may remember, as Copernicus's De Revolutionibus. Vesalius showed two things in general. One, he pointed out the errors of Galen, the famous Greek physician who lived in Rome. Galen had had problems with anatomy because the ancient Romans had extremely strong strictures against the dissection of dead human bodies. So he dissected monkeys and dogs and then extrapolated to the human system. Vesalius instead, as in the late medievals, dissected human corpses. Usually the corpses of executed criminals. That's often where cadavers came from at this time period. The other thing that Vesalius does is he elevates the status of the anatomist. In general, physicians, doctors didn't go in with the scalpels and do the dissections themselves. They had servants doing the dissection, sometimes butchers, barbers, that sort of thing, to do the dissection, and then they would watch or lecture from it. But Vesalius proposes getting his hands dirty, or bloody in this case, by doing the dissections. And this is very clear by the way he presents himself in his own book. The interest in dissection in the 16th and 17th century developed into something which we today would probably find quite remarkable. That is the popularity of the dissection theater as a kind of public entertainment. These dissection theaters were built in Italy and in Holland in particular, but all across Europe, and people came from the town, often upper middle class people, upper class people. It was a social meeting place partially, but they also went to watch these dissections. These were very popular things to attend. Crowds of people would attend to watch a dissection. Well, in the 17th century, as you might well imagine, mechanists were very much drawn to the study of anatomy. They hoped that good anatomical dissections would show the clockworks, the mechanisms by which the bodies functioned. On the other hand, vitalists questioned how useful anatomy really was. It could tell you about the parts of the human body, but if you're a physician, what you're really interested in is life, isn't it? You're interested in preserving life. So why are you dissecting a corpse that doesn't have the very quality you're trying to study? For a mechanist, a body, a corpse, is just a clock that's run down. So you can open up the back of the clock and look at the pieces and how it goes together and imagine it running. For a vitalist, the most important piece is missing. So there's naturally not as much utility, in a sense, to anatomy. Another important development, besides Vesalius, in life sciences and in medicine, is the theory of the circulation of the blood, proposed by William Harvey in 1628. The notion of the heart acting as a pump sounds very mechanical, and in fact, when the idea of the circulation of the blood was published and Descartes found out about it, Descartes was very thrilled for two reasons. One, it's mechanical, so the heart becomes a pump pushing the hydraulic fluid, the blood, through the system, but also the blood's moving in a circle, like a Cartesian vortex, essentially. It's a circular motion. But Harvey was by no means a mechanician. He was a vitalist in the sense that he saw the blood as the seat and the vehicle of life. Life was in the blood. It wasn't just a machine, there was life in the blood. Harvey was also, in many ways, still an admirer of Aristotle. He's an Aristotelian in many, many ways. And so Harvey works as an example of how all these different cross currents in the 17th century are still in existence and still quite useful. When we were talking about Galileo for the first time, I mentioned what he discovered with the telescope. And we talked a little bit about instruments and how instruments are useful in scientific inquiry. Well, there's an instrument that's important here as well, and that is the microscope, another optical instrument. It led to a study of the fine structure of plants and animals. One of the most famous microscopists is Antony van Leeuwenhoek, who lives in Delft in Holland. He's a craftsman, actually. He comes from lower class roots. He's not a sort of the virtuoso gentleman with lots of money to carry on his trade, or rather his studies of the natural world. Instead, he runs a draper's shop, and he makes microscopes himself. But throughout the second half of the 17th century, many, many people, even royalty, come to visit him to look through his microscopes. He made about 500 microscopes. About 10 of these still survive today. He looked at all kinds of things. Spermatozoa, a very famous study of that. He was very interested in reproduction. Saw bacteria, looked at the small structures of various plants and animals. Very fertile worker who wrote lots of letters to societies around Europe. Another person, this time an Italian, Marcello Malpighi, lived at about the same time as Leeuwenhoek, and he studies the lung. When he studies the lung, what he sees for the first time are capillaries, which Harvey was not able to see. In other words, how do the veins and the arteries actually connect? But using the microscope, Malpighi sees capillaries in the lung, thus proving Harvey's theory of the circulation of blood for the first time. Leeuwenhoek does the same thing in 1688 by looking at the tail fin of a living eel. And he can watch the circulation through the capillaries that way. Well, let me get back to Malpighi. What Malpighi's really interested in is trying to discover the mechanisms in living systems. Now, animals are a little bit too complicated, so he looks instead at plants. And he spends a lot of time looking at the structure of plant matter and how plants move, the tubes in them that have fluids flowing through them hydraulically in a very mechanical sense, the building up of the cell walls like bricks, the way a building is put together. He's interested in relating structure and function, and he uses the microscope to see the microstructure, hoping to see also the microfunction, how this clockwork actually works. Many natural philosophers hope that microscopes, as they improve, will finally reveal even atoms, be able to see the atoms and prove the mechanical hypothesis, the mechanical philosophy. That doesn't happen. When it becomes clear that there's a limit to how strong they can make microscopes, how powerful they can make microscopes, and we're still not revealing atoms at the most fundamental level, interest in the microscope actually wanes very quickly, which is interesting to see that the interest in the microscope and the telescope rise throughout the 17th century when people realize that the microscope really isn't going to answer the questions that they hoped it would. Interest declines while the telescopes keep getting bigger and more expensive. Microscopes come back eventually, but not for quite some time. Well, let's get back to this issue of mechanism versus vitalism, now that I've given you some background to where vitalists and mechanists would lie in the life sciences. Other world systems concurrent with the mechanical philosophy gave little, if any, consideration to mechanisms. And we have to remember that some of these were equally influential. The one that comes to mind first is the chemical worldview of the Paracelsians, who saw the whole world as this active mass of forces and chemical activities. The world as a great distilling pot, the universe as a distillation, even the human body as in these chemical terms. Paracelsus' ideas and his followers' ideas were full of a vitalistic notion of a life force, of living things governing living bodies. But rather than spending a lot of time on Paracelsus and the Paracelsians, the person I'd really like to talk about is someone influenced by Paracelsus, but who develops his system more, and I think in more interesting ways, frankly. And that is the Flemish natural philosopher Johann Baptista van Helmont. Van Helmont was born in 1579 in Flanders, and he dies in 1644. So he's living at about the same time as Galileo, a little younger, but at about that time. He lives a couple years past Galileo's lifetime. Van Helmont was educated in a university. He was educated at the University of Louvain, but he refused initially to take a university degree because he thought that everything he learned was worthless. Now, this is a trope. It's a rhetorical trope that comes up again and again with 17th century figures. Descartes says almost exactly the same thing. Descartes is educated at the Jesuit school of La Flèche, and when he starts out his philosophical inquiries, he says, well, eventually I realized that everything I learned was wrong, and so I'm going to start over and build it up again. Yes, well, if you read Descartes very carefully, you realize that he learned his Jesuit scholastic education very, very carefully, and he keeps using part of it as a methodology. The same is certainly true of Van Helmont. He rejected vociferously, even much more vociferously than Descartes' scholastic method, Nonetheless, he was university trained. He learned this stuff. Um, Bacon's another example. Rails against the university, rails against the scholastics. But you know, even his followers, the universities are still being run by the scholastics, so many of these people still cut their teeth, if you will, on traditional scholastic education. Well, Van Helmont was an equal opponent to Galenic forms of medicine and to scholastic Aristotelian natural philosophy. He disliked both with pretty much the same intensity. Maybe not as intense in some ways as Paracelsus, but there's some of this Paracelsian vitriol, if you will, in Van Helmont's writings as well. He even assails Aristotle for reducing the world to the status of a machine, because even Aristotle, with his what I've called a biological type worldview, doesn't realize the depth to which vital forces play an active role in the universe. Well, Van Helmont's worldview is a very interesting and highly influential, I might add, combination of mechanism with vitalism. What he does, first of all, is he divides all material changes into two categories, the superficial and the fundamental. The superficial changes are what we ordinarily see in the chemical laboratory. I haven't said much about what Van Helmont does for a living. He's a physician. He's very interested in chemistry. He spends a lot of time doing chemical experiments, and we'll talk about some of his experiments in this lecture. This superficial kind of change is most of what we see in the chemical laboratory. It happens when mechanical changes are involved with particles or with corpuscles, with parts of matter. Let me give you an example. We can take mercury, let's say, the metal mercury, and dissolve it in an acid, and it becomes transparent from being a silvery metal. We could boil that solution down and heat it, and we'd get a red powder. It's still the mercury, but it's got a different kind of appearance to us. It's been changed somehow mechanically. If we take that red powder, mix it with charcoal, heat it up, the mercury that we started with, we can recover. So the mercury was never really altered. According to Van Helmont, it has assumed what he calls a larva. Larva is the Latin word meaning mask. So the mercury has taken on these various masks. We see it first as a silvery liquid, then as a transparent fluid, then as a red powder. Finally, we strip the mask off, and it's back the way it started. These are all superficial changes to him. These are just masks, and these are mechanical for him. It's a rearrangement of parts of the corpuscles. Fundamental changes, on the other hand, depend upon the action of two things, what he calls the semina and the archaea. The semina, those are seeds, just a simple word of seeds. These are seeds of change in things. The archaeus, plural archaea, are regulating spiritual entities that life processes depend upon. Let me talk about the archaeus first. The term is actually borrowed from Paracelsus, but Van Helmont develops this idea of an archaeus a bit further. The archaeus governs the proper functioning of living bodies. It oversees, for example, the digestion of food. We take in all this food, it's digested and nourishes us. The way that process is overseen is by the action of the archaeus. The archaeus also keeps the body functioning properly. When the archaeus is weakened or goes out of order or has some other problem, we become sick. So medicine should cure people by strengthening the archaeus, not by trying to cure the symptoms. Say you have a fever. Don't try to cure the fever, because that's just a symptom of a weakened archaeus. You have to do something to strengthen the archaeus, and the archaeus will put the body back in the proper order. One of the most interesting things, I think, that Van Helmont talks about is how the archaeus can be weakened by imagination. He writes a work on the plague, very contagious disease, ravages Europe for centuries. And he says, why does the plague seem to pass from person to person? It's contagious. It propagates at a very rapid rate through the population. It's because people are so afraid of the plague. Their imagination instills such fear that the archaeus itself becomes weakened, and afraid, and therefore their imagination creates the sickness by weakening the archeus, and that's how plague actually propagates. Very interesting idea. Now, the archeus, there's something commonsensical about it. There's also something rather weird about it. But before you dismiss it as being just too weird, let me go out a little bit on a limb here and say that if you read between the lines, if you read carefully popularized versions of genetics, particularly things dealing with DNA, DNA becomes, in a sense, a modern archeus, because we tend to attribute everything that happens to a body to DNA, even though there's no mechanical way that DNA could, in fact, explain certain things that are attributed to it popularly. I'm not saying by molecular biologists, but in popular redactions of DNA, molecular biology. DNA does, in effect, become a governing archeus, in a sense, a lot like Van Helmont's. Fundamental change in matter comes about by the action of semina, that is, these seeds. These seeds act upon matter and form it into different substances radically. For Van Helmont, there is one single substance in the world, one fundamental substance, and that substance is water. Now, if you think way, way back to the very second lecture I gave, you'll remember Thales of Miletus said the same thing in the 6th century BC. So this is partly a revival of the ancient doctrine of Thales that everything is made of water. For Van Helmont, however, he also gets it by reading the first chapter of Genesis, because in creating the world, the Spirit of God hovers upon the waters. The waters, the waters from which creation and everything springs by the action of the seeds that God implanted in the world. The Hebrew word there, as Van Helmont knows, is the same word as what a hen does to its eggs. It broods upon its eggs. The Spirit of God broods upon the waters. So there's this sort of vital, seed-like, egg-like implication there, and Van Helmont picks up on this. These seeds, again, or seminal principles, are active principles. They actually do stuff in the world. They organize water into all the different substances that we see. This is not superficial change. This is not mechanical change. It's a fundamental change in the nature of the water. Their action radically transforms water into everything else. God has implanted these active principles in the world. You may remember my also talking about St. Augustine and the idea of the rationes seminales, the seminal reasons. This is very closely related to Van Helmont as well. Augustine's idea is that God implants these seeds in an instantaneous creation, and over time they develop and produce changes in the world, development in the world at specific times and places. That's again related to this. Well, what kind of proofs does Van Helmont have? One of his many proofs for his water theory is a very famous experiment called the willow tree experiment. He takes a big vat of earth, which he weighs very exactly, several hundred pounds, a couple hundred pounds of earth. He dries out the earth and weighs it. Then he plants a willow sapling in it, which he's also weighed, and he waters it. He waters it he does this a couple of times, but in one experiment, it's for 5 years. He keeps watering it. At the end, he uproots the tree, scrapes the soil off. He finds that the tree weighs over 300 pounds now. Takes the soil, dries it out, and finds that the weight of the soil has changed by only about 2 or 3 ounces. Therefore, the entire weight of the willow tree that he's weighed, not including the leaves that it's dropped in the fall, has come about entirely from water. And if you put this willow tree through a chemical experiment, put it in a distilling flask, chop it up and distill it, you can distill out of it oils, and you can get salts and all kinds of different chemical substances, but the only thing that's been added to that dirt was the water. Therefore, he concludes that the seeds, the semina within the willow tree, radically convert the water that he's been watering it with for the 5 years into all the substances in the tree. Now, another thing that's important for Van Helmont is that action at a distance is not a problem, as it is for Aristotle, as it is for the mechanists. The semina could extend their influence to objects without the transfer of material substance. They can organize and change matter without actually being in physical contact with it. One of the illustrations he uses of this is a very curious idea known as the weapon salve. Weapon salve, the armarium unguentum, the unguent for weapons, is a way of curing wounds. But instead of slathering it on the wound, you put it on the sword that made the wound, and it cures the wound at a distance. Now, how does this happen? Well, because you can't just put it on any old sword. You need to put it on a sword that has the blood of the person who was cut. You could also take a piece of cloth. As long as you have some of the victim's blood, you mix this with the weapon salve, and the weapon salve cures the wound at a distance. How does it do this? Well, because it acts upon the blood. The blood has a natural, vital, sympathetic connection with the person who was wounded. And so if you affect the blood, you affect the wound, you heal the person. It's an action by sympathy. In fact, Van Helmont prefers to borrow a term, which he presumably gets from Gilbert, that it's a kind of magnetism. Just the way the magnet attracts iron, the North Pole attracts the compass needle, so too there's an action through space of the weapon salve on the wound. Now, curiously, more people tried to explain the action of the salve than actually tried to try out its efficacy. We like to sort of chortle at something like the weapon salve, but if you think about it, actually it probably did work in a lot of cases, because the thing you have to do when you're using the weapon salve is you clean the wound, rather than plastering it with some concoction with hog lard and various other things which would cause infection. So in fact, probably you were better off trying the weapon salve than trying other kinds of unguents. The weapon salve was also treated by mechanists, though. This is a very interesting thing. Gassendi talks about the weapon salve at length, and he explains it rather than by properties of sympathy or action at a distance. He explains it entirely mechanically. He says, for example, and you can do this experiment at home, take a candle. I think Gassendi uses a torch for this, but use a candle, it'll work just as well, and blow out the candle. Do it in a calm room where there's not a lot of wind, and you'll see a thin trail of smoke come up from the candle. Now hold a lit match in the light, in the trail of that smoke, and you'll find the fire zips back down the smoke and relights the candle. Well, Gassendi says that's how the weapon salve works, because there's an invisible trail of corpuscles connecting the blood, or the blood on the weapon, with the wound. You put the weapon salve on the sword, and its corpuscles create an effluvium that travels back along those corpuscles, just like the flame along the candle smoke, to heal the wound. It's very interesting how you can take this example of the weapon salve and talk about it in two entirely different ways. Explain it two entirely different ways. In fact, the explanation of occult phenomena, that is, phenomena that don't have obvious reasons for why they occur, was an important testing ground for the mechanical philosophy. Seeming actions at a distance, such as magnetical attractions, electrical attractions, and repulsions, become, for the mechanists, always the result of effluvia of particles streaming out of things and how those particles interact. And thus, these actions, these examples of action at a distance, by being converted into the action of effluvia, rather than being stumbling blocks for the mechanical philosophy, become instead proofs for it. It's an interesting way they turn this around. However, at the same time, I have to mention that failures of mechanism were often patched over by the importation of active principles from more vitalistic systems into mechanism. Gassendi does this himself when talking about, magnetical attractions or electrical attractions, the way a piece of amber, if you rub it on cloth, will pick up pieces of paper. Well, how does it do that? Well, Gassendi says, well, it's sort of like fish hooks. There are these lines that are shot out that hook into, mechanically, hook into the paper and draw it back to the amber. Well, that's fine at one level until you ask, what's doing the drawing? What's reeling in the line, as it were? That's not something mechanical, is it? Right? You can't explain that by an effluvium of particles. As it turns out, mechanism, particularly in England, by the way, perhaps by the influence of Gilbert and others, becomes really full of active principles that are acting in matter. Sometimes these are a bit obscured, but nonetheless, there's this whole continuum, as I tried to say at the beginning, between vitalism and mechanism. And so it's important to bear in mind the rich variety of ideas and systems coexisting in the 17th century. We don't want to exaggerate the separation of ideas one side or the other, but rather look at them in their context. And in this case, vitalism versus mechanism provided two pots from which to take components to compose various systems.